In this video, I'm intending to cover two examples of sort of word problems that can involve an infinite geometric series. And in both cases, I really think that the key to getting them right and to working through them is to sort of taking notes about the problem, writing things down, and recognizing where the geometric series is. Because if you can see the geometric series, we know the formula is simple. I mean, the formula we know is that the infinite sum is supposed to be the first term over 1 minus the common ratio. So if you can figure out where it starts and what the common ratio is, you're done. Okay? So this first example, a bouncy ball, which is known to rebound 70% of the height it falls, is dropped from a height of 10 feet. Find the total distance traveled by the ball from the moment it's first dropped to the moment it stops moving. So the idea here is, if you've got the ground and you've got a ball that's dropped from, a height of 10 feet, right? How far is the ball going to move? Well, we know it's going to fall down 10 feet, right? Then what happens, right? What happens next is the ball bounces, right? How far up does it go? Well, we know it's supposed to rebound 70% of the distance that it falls, so it's going to bounce back up. And some people might say, oh, well, I can tell 70% of 10 feet is 7. And that's true, but it might be easier for us to see this as 10 times 0.7, because that's how much it's going to rebound, right? So that's how far the ball goes back up, right? Then what happens? Then the ball goes back down again. So in total, in the sort of red part of this arc, it would make sense that the ball actually traveled twice that 10 times 0.7. It traveled 7 feet up and 7 feet back down, right? So that's how much it travels there. So again, what happens next, right? When the ball hits the ground here, it bounces again. And when it bounces back up, how far does it go? The idea is it's going to go this far, this 10 times 0.7, but it's going to be 70% of that. So it's 10 times 0.07 times another 0.07, so 0.07 squared. And again, it's going to fall down that distance as well, so we'll have 2 times that. Hopefully you can see where this is going. I'll write out one more of them just to make it clear. When the ball bounces again, how high is it going to be this time? Well, again, it's going to be this distance, this 10 times 0.7 now cubed, and again times 2, because the ball is going up that distance and also back down that distance. Right? So now what I want us to do is I sort of want us to take all of this information and sort of write it again so we can see it. By the way, the ball is going to keep doing this, right? It's going to keep falling and further and smaller and smaller and smaller amounts. What we need to look at is, in total, how far is the ball going to travel, right? So we have the initial 10 feet, which is kind of an oddball. I'm going to leave that off to the side. Then you've got this 20 times 0.7 plus 20 times 0.7 squared plus 20 times 0.7 cubed. And hopefully you can see, hey, we have a geometric series here. This is a geometric series for which the first term, for which your u1 is 20 times 0.7. And what's the common ratio of this thing? Well, each time I'm multiplying by another 0.7, and I'm multiplying by another 0.7 because the ball is only rebounding 70% of the distance, so 0.7. By the way, I haven't forgotten about this thing. Notice this is only geometric if I'm only looking at the parts where it's bouncing both up and down, up and down, up and down. In fact, this single fall in the beginning is a little bit of an anomaly. So what we're going to do is we're going to sort of add up this infinite part, and at the end we'll just add on the extra 10, right? So let's use our formula at this point. The infinite sum is supposed to be u1 over 1 minus r. So in our case, that's supposed to be 20 times 0.7 divided by 1 minus 0.7. So that is 20 times 0.7 over 0.3. And I mean, we can do any number of things to simplify this. I'm trying to do this without a calculator. I'm looking at this being, let's see here, I guess that's 14 on the top and 0.3 on the bottom. If you move that decimal place over, you'll have 140 over 3. And that's the distance that it travels in the up and down motions. Remember also that we're going to have to take that and add 10 to it. So our total distance will be the 140 over 3 plus the original 10 that it fell. And this is our total distance traveled. But we can do a little bit better than that in terms of making it prettier. If you get a common denominator, this will end up being 170 over 3, which in the calculator is 56.6 repeating. Okay, so any of those answers would be acceptable on the exam. In this next example, I want us to write this repeating decimal as a fraction in its simplest form. And you know, I'm sort of giving you the hint that we can do that by writing the decimals in infinite geometric series. And so, surprise, surprise, I'm going to do something kind of sneaky here. I'm going to take that number, and however it repeats, I'm going to break the number into those pieces. So the first part I'm going to write is 0.12, because that's the first repeating segment. The next repeating segment is the next 12, but it's over sort of another 2 decimal spaces. It would be plus 0.0012. Right? And the idea is, imagine if you added those two numbers together, like if you were to stack them on top of one another, you'd end up with 0.1212. So that's not the whole thing, but it's the first 2 repeats. The next one, we'll do 0 point, and I'll have zeros in the first 2 places because I've already written the first 2 places here. I'll have zeros in the next 2 places because I already have the next 2 decimal places here, and so I'll have 1, 2 as my next one there. Right? And so the idea is I've taken this number, 0.121212, and expressed it as repeats of itself. Right? So now the question is, do you recognize that this is a geometric series? And I hope that you do. I hope that you recognize, hey, wait a minute, I learned somewhere in grade school that when you multiply a number by like 0.01 or by 100 or by some, one with some zeros after or before it, it moves the decimal place. So the idea here is that notice the decimal place is moving 2 places each time. What that means is you are multiplying by 0.01. In both of these cases, you're multiplying by 0.01, right? So, wait a minute, this means we have a geometric series whose first term is 0.12 and whose common ratio is 0.1, right? Well, wonderful. If I have this information, I can then say that the infinite sum of this, if I were to continue doing this forever, the infinite sum of this thing is the first term over 1 minus the common ratio. Sorry, that was a little bit ugly there. 1 minus the common ratio. So great, I'm just going to plug in the information I have and figure this out. This means I have 0.12 over 1 minus 0. I just realized my common ratio up here is wrong. This should have been 0.01. Please forgive me on that one. So this is a 0.01 down here. Means I end up with 0.12 over 0.99. And so if I move the decimal place in both of those, I end up with 12 over 99. Both of those can be divided by 3, and so your final simplified answer ends up being that it's 4 over 33. 4 over 33 is equivalent to 0.12 repeating. Okay? I might as well mention one other thing while I've sort of got your attention here. What if the repeat up above had been 3 decimals? If it had been 1, 2, 3, 1, 2, 3, 1, 2, 3. 0.123 would still have been the first term, but the common ratio would not be 0.01, because if it was 1, 2, 3, 1, 2, 3, 1, 2, 3, the decimal place would have to move 3 places every time. Your common ratio would have to be 0.001. There will be an extra 0 in there. So in case you see one of those in the homework or on a test or something, that's the deal with that one. There you go.